We just reviewed some true, false and multiple choice questions. Let us now move to some problem types. I am numbering question 1, 2, just like we are here. They are not number 1, 2 in any quizzes, in any midterms, in any other place. So let us see this problem. A stress strain data and graph obtained from tensile testing of a steel are shown below. Determine the following for this steel: yield strength, ultimate tensile strength, modulus of resilience, and plastic or permanent strain at fracture. So these values are also given and this graph is also given, right? So as I always request you, though you have done it earlier in some quiz or so on and so forth, but if you want to really practice well for your final exams and so on, then please don't go further. Just take your pen and pencil and so on and a rough page and start solving it again. This is always a very good practice. If you want, if you think you are 100% sure of what is to be done and so on, you can go to the next page of solutions, but otherwise you solve it again. It gives you a very good feeling. Okay, so let us see. So I am showing you just the graph now, and you see this is the straight line, and from here you start the curve. So this is one of those curves we have specially constructed. This is a real material, by the way, where the end of the straight line is very clear that this is at 500 megapascal. The end is very clear, 500 megapascal. So you don't have to do any 0.2% yield strength and so on. It is very clear on this graph that this is the yield point. Similarly, the ultimate strength is the highest point on the graph. So if you go, it touches this 900 line. It touches the 900 line. So this is also very clear. This is not giving you all, right? It is not giving you the rest of the remaining values until 900. It is giving you until 662. So it is giving you until here roughly, the data table. But that is for another reason. From the graph, the yield point is this 500 megapascal and the ultimate is roughly 900, right? Now the fracture point, the point at which fracture happens, you take a horizontal line, and you find the value, that what is this value, right? Similarly, you drop a vertical line from here and you will see that it cuts exactly at 0.08. So the strain at fracture is 0.08. A strain at fracture is 0.08. So the things that you can find from here: yield point, ultimate point is direct, fracture strain is direct, but fracture stress we will have to find out. Okay, so now these you can do from here and then maybe some calculations. So I am just showing you here again in a smaller one, just for so that you can see, and showing that yield point is roughly 500. I have not used equal to because we are reading, so we are saying it is approximately 500. I am saying ultimate strength is approximately 900, which is there. Now modulus of resilience is area under the elastic part of the graph. Remember, right? Area under the elastic part. This elastic part is a straight line. So if you draw a vertical line here, then this triangle, the area of the triangle, area under the elastic part of the graph. So area of the triangle. For any triangle, you know that triangle area is half base into height, right? Half base into height. So half will be there. The base is a strain at this point and the height is a stress at this point. So this is the yield point. Therefore, half yield stress and half a strain at yield. Now, if you try to drop a straight line here, you will get an approximate value. But here in the data table, it is given that at 500, the strain at 0.0025. So exact strain at the yield point is given. Therefore, half a stress into strain 0.5, 500 megapascal, 0.0025. Remember, this is very, very critical. Many of you keep on doing these small errors all through. Write everything in the basic unit. Don't write it 500, right? Write as 500 into 10 raised to 6. A strain, of course, does not have any unit. So this comes out to be 625000 Pascal. Now either write it as 625 kilopascal if you remove 3, or 0.625 megapascal. But until here, this unit system of Pascal or kilopascal or megapascal is not right. It is there, but it is not right. Why? You are finding modulus of toughness. Toughness is energy per unit volume. Toughness is a specific energy. It is energy per unit volume. That is what we told you. That is why in impact toughness, you measure it in joules and so on. So you can write megapascal, but the main thing is that here it is joule per meter cube. Megapascal can also be, I have told you earlier, Pascal. Pascal is Newton upon meter square. If you multiply it by meter, then it will become Newton meter upon meter cube. And Newton meter is joules and meter cube is meter cube. So you can leave it at a megapascal, but if you do that, then sometimes I'll put a small minus half there to point out to you that engineers, science people should know the correct units of everything. If the correct units are not there, it is just a number. So because toughness is an energy thing and it is a specific energy, it is energy per unit volume. So this is the answer. For the last thing, plastic strain, but plastic strain at fracture. Now, many of you did this, unfortunately, which means that we did not go through the lectures properly, the video lectures or the lecture notes and the problem solutions. You drop down the line, this is 0.08. This is the total strain at fracture. At any point in the plastic region, any point here, for example, if you drop down a vertical line, you get the total strain. But if you draw a line parallel to the original line, then from here to the end was the total strain. From here to the end of the parallel line was the plastic strain, and the remaining was the elastic strain, which is lost. That if you remove the load, then the elastic portion of the strain will be lost and only permanent one will be the other one. So here we are asking the plastic strain at fracture. So the thing is that yes, you drop a vertical line, this is one thing, but then you try to make a line parallel to this one. So I am asking that from this point, from here until this point, the parallel line, what is the strain? That is the permanent plastic strain. So you have to find the elastic portion of the strain, subtract it from the total. Now again, there are two things. Either you have the graph, you enlarge the graph, you draw a very good parallel line and see where it cuts. But there is a much easier way. You see, if this is a vertical line and you have this line, now the slope of this line is exactly the same as the slope of this line, which is E, the Young's modulus, right? So if you have calculated the Young's modulus already, then you can use it. If you have not calculated it, then you can find it, right? But if you know the Young's modulus, then the slope is there. So let us see. I am saying plastic strain at fracture, which I am saying strain plastic at fracture. Is strain at fracture minus the elastic strain at fracture. So strain at fracture is 0.08, no issue. But elastic strain is simply the stress at fracture divided by E. Remember, sigma is equal to E epsilon. Whenever there is the straight line region, if we convert it into the straight line, right, that line is a straight line and we know the slope is E. So sigma is equal to E epsilon. Therefore, epsilon is equal to sigma upon E. So this is the elastic value for the fracture point. Therefore, fracture stress divided by E. So this direct fracture strain is 0.08, the fracture stress, if you had found out, was 662 roughly, right? You read it correctly, if you have read it correctly. If it was given in the table, if the full table was given to you in the problem, right, then this point I wrongly said perhaps a little while earlier that this is not all the data points, but I am sorry, I take that back. If you read it, it goes 845, 892, 897. So it goes all the way up and then comes down. So it means, yes, it goes all the way up, and it is clearly that at fracture the strain is 0.08 and the stress is 662. So you don't have to even make a horizontal line. This stress of 662 is there. So this is there. Now what is the E value? Right? What is the Young's modulus? So the easiest thing will be that you go back to the initial line. You go back to the initial line, right? The initial line, this stress is 500 and a strain at 500 is 0.0025, right? So 500 minus 0, the stress value, and a strain is 0.0025 minus 0, right? Because if there is the straight line, you want the slope. So the difference in the stresses between 2 points and the difference between the strains at the 2 points. So very accurately, you take the initial point and the final point. So 500 minus 0 for a stress and 0.0025 minus 0 for a strain. So divide 500 by 0.0025, you will get 200 gigapascal. So now this is it. Now you have everything. So now this is the plastic strain at fracture. This is not directly the strain at fracture, right? So all other points were rather very easy, but still Young's yield point, you can directly read. Ultimate strength, you can directly read. For the toughness, modulus of resilience, you want to find the area under the elastic region, end of the elastic region. So you take yield point as your point and you say half sigma into strain. And for plastic strain at fracture, you have total strain at fracture minus elastic strain at fracture. So, right. So if I can almost challenge you, I can't say I challenge you, but I can guarantee you or whatever that if one problem like this, we have done other problems on stress strain which were good, but this one problem also is a very, very good example. If what we have done just now, if you really understand what we were doing, then almost any problem in a stress strain will be easy for you to do. Okay, good. Next question. This is also a question about material properties. Plot of yield strength versus grain diameter raised to minus half. Right, grain diameter raised to minus half means 1 upon root, right? So plot of yield strength versus this for a 70 copper 30 zinc cartridge brass is shown. So this is a copper zinc alloy in which the percentage of copper was 70% and the percentage of, so this is an alloy, this is called cartridge brass, and yield strength on one side and D raised to minus half on the other side. So this graph is given. Determine the Hall pitch equation constants sigma naught and K for this material. Now find the yield strength of this alloy when the average grain diameter is 2 into 10 raised to minus 3 millimeter. Okay. So just point that in your actual quizzes and exams and so on in this course, we give you the full formula sheet. So any formulas in the course are given. You don't have to memorize any of the formulas, and any of the material values that you need are either given in the question or they are given in a property table which will be given to you together with the formulas. So you don't have to memorize anything. All the values of material properties will be there. All the equations will be there. So if you don't remember the Hall pitch equation, you just see in the formula sheet, but don't look anywhere else. So again, it is a practice thing. You can solve it again now to get good practice. If you are very sure of your solution, then you should go to the next page.